Yeah, let me share my screen. Okay, so let's get started. And today, I will present the paper about the statistical cost of the adaptation in multi-source transfer learning. And some of the highlights for that paper. The first thing the paper characterize the statistical hardness of multi-source transfer learning, and they introduce uh, an, a definition of the intrinsic cost of adaptation, meaning that the cost is like it derived from the problem itself, regardless of the algorithm to estimate the estimator. And it is like an error, the ratio between the error of the when we know the bias and we don't know the bias. And the next thing, based on the cost of adaptation, they specify when general adaptation is possible and impossible. And general adaptation meaning that there's no assumption on the bias. And in case the general adaptation is impossible, and they introduce some restrictions for the bias, for the structure of the bias, and provide some methods to construct the target estimator. Okay, so then let's start with some basic notation. So for the multi-source transfer learning, so we have multi-source like n plus one domain, and the first domain k equal to 0 means the target domain that we would like to estimate the parameter for that domain. And we have m source domain, and each one contains a set of data that's ki. And for each domain, we have one underlying distribution, pk. Pk is the distribution for the k domain, and the data dk is sampled from the underlying distribution pk. And for each domain, we have we want to estimate the estimated theta, and theta star is the true estimator of the domain k, and that estimator is derived by a distribution function t that maps the underlying distribution to the parameter of the estimator. And our objective again is to estimate the domain first, the domain estimate the theta star for the target domain k equal to 0, choosing all of the data from all domain. Okay, so that is some basic starting point. And we also have a definition of the well-behaved domain-specific estimator,
Wait, I
which
have a
means that,
question.
yes, please.
Uh, I'm not familiar with the setting. Could you go through like what is what's the point of this? What is transfer learning in general? Like,
Um, you
yeah,
mean transfer learning in general?
just some motivation for this problem.
Right.
So transfer learning in general means that you have a data in one domain and you want to transfer the knowledge of that domain to another domain that's called the target domain. So you have source domains and you have a target domain, and you want to take advantage of the data from the source domain to have a better estimator for the target domain.
Okay, thank you.
Yeah.
Yeah, the motivation is to just to reuse data from multiple sources to make learning estimation faster. And we do that all
Yeah.
the time in practice, right? You barely learn from scratch.
Yes, that's right. Like in application, uh, like it's very common to have some pre-trained model on, for example, like pre-trained on the like large language model is kind of a pre-trained model, and you apply to other tasks, and it's called transfer learning.
Mm.
Yeah, so the next definition we have is well-behaved domain-specific estimator. So an estimator equal well-behaved if the title theta is called a well-behaved if the distance between that estimator to the true estimator of the k-domains is like the probability of that distance greater than t is bounded by a sub-Gaussian. And some note for that definition, like the first thing, the title theta k can be seen as a random variable. So that's the reason why they introduce sub-Gaussian and the probability in the definition. Because like from an underlying distribution pk, so we have the data decay sample from that distribution, and the estimator title theta k is learned from the data decay. And the assumption tells you that
What
like
is tau?
uh,
Constant. It's a
tau,
constant, I think.
tau I think it's a constant in the sub-Gaussian. Like
That's fine.
the probability here means that like the probability of the distance greater than t is bounded by the Gaussian.
Okay.
Yeah, and the assumption, like another thing is the a in calculating the distance. So it's a projection to another space. So it tells you that like under every projection, the distance is smaller than the threshold. And there are some examples of the problem in which the well-behaved estimator exists, such as the normal mean estimator or the linear regression. So I don't present it in detail here, so you can refer to the main paper for like the description. Yeah, so the next thing is the oracle minimax rate. So like the oracle here means that we have access to the bias. So in general, the bias between the domain are unknown, and the oracle minimax rate is the one that has access to the bias. We have a definition here is the class of a local parameter. Like so we have the H here is the bias configuration, and the class of local parameter is a set of parameter that whose the distance of the k domain of the estimator of the k domain to the target true estimator is smaller than the sk. Sk is a scalar, which so in general we usually have like the distance between two domains, and the definition like the class here provide about on the distance to the target estimator. And we have an assumption that the two local estimator are assumed to be in the class O.
Excuse me,
Yes.
I don't understand this part. Like, what is the theta zero here? Like, which is only one parameter to estimate like all of the domain, right?
No. So we have n plus one domain, and k equals to 0 means the target domain. And for each domain, we have a true estimator.
Okay, so like we have one domain, the target domain, and the rest are like a source domain.
Yes.
Okay.
So k equal to 1 denotes
Okay.
k equal to 0.
Yeah, sorry,
Yes.
I didn't pay attention to that part. All right. But like why does the bias conversion constraint in like 0 and 1?
Can you repeat the bias
Why?
constraint?
Yeah. Why does the bias constraint in 0 and 1?
It's a range, like the bias configuration is a value between 0 and 1. It can be 0.5, 0.6.
But like it's the upper bound of the like a grid distance of
I think in that paper they like have an assumption that the parameter of the estimator is from 0 to 1. So
okay.
I think that the distance is bounded by 1. So that's why the
Okay.
bias configuration has
Yeah.
is between 0 and 1.
Yeah, so bounded parameter space.
Yeah, it's just bounded and they normalize it. So it
Okay.
just constant. 0 and 1 for convenience.
Yep. Okay, so the next definition is a probability class, like with general bias structure. So for each configuration, bias configuration H, in the sample size of O domain, n 0 to nm, and the constant tau and c tau in the well-behaved estimator definition, we have a function like the probability class P, like it's the class of joint distribution on the uh, on on the estimator. So the estimated title theta k is sample from a distribution P belong to that class. And there exists a set of parameter like the true parameter in the class of local parameter. That's like that's the 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 estimator from the derived from the distribution satisfy the well-behaved property to that set of two parameters. And we denote the true like the estimated estimator for the target domain as when the bias configuration H is known as the hat theta 0 with emphasize on the H here. So it's derived from the set of the estimated local estimator title theta k, and the bias configuration H. Okay, so the next is the R minimum rate. The first thing is like given a subset of the domain S, so it's great like contain the target domain, and it's a subset of the source domain. And the range function R is the minimum over S of the value d tau square over ns. So the d here is the dimension of the estimator. So the estimator has d parameters. So the whole term here is d tau square, and s can be seen as the variance, and the 8s here is the maximum value of the bias configuration in that set of the domain. So the S square here is the bias. And with yeah.
So what does this result mean?
So this result tells us that the minimum rate.
Oh, so the definition, equation 3, the definition, right? Not the result.
Yes, so it's the definition of the rate function R, and the equation 4 is the result.
Okay, I see.
Like yeah, so the equation 4 it tells us that the expected uh, MSE between the estimated of the target estimator theta hat 0 8 here to the true estimator theta star 0 is bounded by the rate function R.
Mm. So can you explain the rate function again, the equation 3, that balances between H square S, that is the bias. The bias is
Yes.
subset. And then what is the first term? D tau square NS?
Yeah, so I have a note here about the bias variance trade-off.
Mm-hmm.
So the D tau square NS represent the variance because the tau is the coefficient in the graph subgaussian. So greater tau means that higher variance.
Mm.
And the D here is the number of the parameter in the estimator.
Mm.
So the parameter type, like the parameter theta, has D parameter.
Mm.
So NS is the total size of the data.
Mm.
So that's the variance. In the H here is the maximum value over the bias, which in the subset within the subset S. So that's the bias.
Mm. So is this here the linear model?
The linear for estimating what?
For the observation. So you have theta and then do you observe X and Y, right? Or Z? So Z?
Yes. So like the data is a set of Z, but that in paper they don't work directly on the Z like the actual data, but they worked on the estimator.
They abstracted away with the well-behaved estimator.
Yeah.
That's a linear one, yeah. Equation 1 because they uh
Yes. So the A here is like the projection and it's linear.
mm, yeah, this is a very statistic uh, kind of thing paper.
Yeah. So it's you mean that it's very abstract, right?
Yeah, this is the language that statisticians they use for proving things. We also use that in machine learning too, in reinforcement too. So it's just
Yeah.
very it's helpful to see what they are doing, the tools they use. But I think these guys, the authors, they are statisticians.
Yeah.
Yeah, but the phenomenon is what we know, right? We just don't know the form. I mean, they find this form is that's amazing, but we know there's some balance between bias and variance when you use data from other sources. So that's the whole story. basically, even with what we're doing right now in hybrid and transfer reinforcement learning. So we kind of want to balance between bias and variance, because every time you use data from other sources, then you reduce the variance, but you induce more bias. So the question is, how can you balance that, and how can you design an algorithm that can automatically adapt to that trade-off without knowing the optimal trade-off? So that basically the very concrete question we want to solve. Of course, in different setting, you have different trade-off. Like in this statistical setting, so this is trade-off. But in reinforcement learning, it's much harder. But still, when we see what statistic doing in the setting, so we get some ideas, some flavors that they use to trick the problems.
Yeah. So I think it's interesting to look at the proof, but I don't have it here. But I think it's interesting to look at that
Yeah, so that
to
is that the
understand.
main result? That's the key result in the paper, right? They say that quantity number three that's characterize the min max rate of transfer learning. Is that all?
I think not all, like it's a key result, but one of the key result.
Mm.
Like later they will like define the intrinsic cost of adaptation, which
Mm.
means that when uh, the bias configuration is unknown,
Mm.
so what could like an algorithm achieve in comparison with when the bias configuration F is known.
Mm. I see.
And we also like specify when the general adaptation is possible and when it's not impossible.
Yeah, that's very interesting. So basically, the number three, it says that so it's not always useful to use data from all sources.
Yes.
Have
And
to
one of
balance.
the
Yeah. The point is about
yeah,
balancing bias and variance. That's the point. Not about just blindly reusing the data from all sources. So that's the
yeah.
story.
And in one of the like some example or like the specific configuration later, like the key point is to choose a subset of the source domains.
Mm. Yeah, how do they do that?
Yeah, I will have one example later. Yeah, we can continue with the presentation, and I have like
Mm.
one example
Sure.
uh, when when they like choose the set of the source domain. Okay, so that's the setting when the configuration F is known, and then we move on the configuration when the F is unknown, and in that case, the F is unknown, but it assumed to belong to the set of configuration capital H.
Mm.
And the first, the intrinsic cost of adaptation, it derived is defined and in equation 6. So consider an estimator theta hat 0 without knowing the true bias configuration F.
Mm.
So it's only depend on the domain specific estimator title theta k for k from 0 to m and the sample size of the whole domain. And the cost of the adaptation for that estimated theta hat is a ratio between between the MSE mean square error of that estimator to the rate function are defined in the previous definition. And the supremum here is taken because we don't know the two like bias configuration A. We only know that it belongs to the to a set. So it tells us that in the worst case, what is the worst ratio. And that's it for one estimator. So for all estimator, the C square F is defined as the adaptation cost of the best estimator. So assume that we have a best algorithm. So what would be the adaptation cost? Yeah, so the meaning of the adaptation cost. So if the adaptation cost divided by the big O one, means that the estimator achieves the oracle rate. Like when we don't know the bias configuration, we still achieve the result as good as when we know the bias configuration. But in general, it's like hard to achieve. So a polynomial or the logarithmic factor is considered as acceptable. Yeah, so with that, we have another definition of general adaptation. So general adaptation means we don't know any information about the bias configuration. So so in that case, the capital S, the set of the bias configuration equal to the set of all bias configuration in the space from 0 to 1. So the C star of C 0 to 1 is defined as the cost of general adaptation. And for with that definition, the next result they have it to tell us when the general adaptation is possible and when it's impossible with a fixed number of source domains. So the theorem here means that when the number of the source domains is fixed and it's greater or equal to 0, and assume that the sample size of all domains are equal. And the cost of the general cost of adaptation, C star of 0 to 1 powered by M is bounded by two constants, the C LM and the CUM, multiplied by the minimum of the N over D and 0. So it means that the relationship between the possibility of general adaptation is linked to the relativity of the N and the D and 0. So if the N smaller than D and 0, it means that the general adaptation is possible. If it's scale larger than N, scale larger than N, D and 0, it means that the general cost of adaptation is unbounded and general adaptation is impossible. And in the paper, they also have the case when the number of source domain is growing, but I don't present it here. So that's the specification where the general adaptation is impossible and possible.
So what does the
So in the case of
what does that result in the previous one? That's me. What does that?
Which section?
Yeah, this one.
In section 4.
Yeah, what does it say?
So the C here is the cost of general adaptation, means that we don't know any information about the bias configuration.
Mm.
And if the sample size n of the sample size of the source domain, if the sample size of the source domains scale with the multiplication of the dimensions and the size of the target domain, so general adaptation is possible because the cost here is bounded. So the CL and CU is constant. So that one is bounded because the n scale with the n zero.
Mm-hmm. But they
So
don't
is it
really-
saying that if you have uh, lots of data, it means that you cannot transfer learning it? Is it what is it saying?
Yeah, I think so. Like
Uh,
the relative the relativity between the sample size of the source and the target domain.
Mm. But the number of it doesn't say how the number of source domains affects the adaptation, right? They don't know the
Yes,
of CU and CL. It's just constant
uh,
depends on M. But what is it polynomial in M or what?
because uh, in that setting, M is fixed, so it's
Oh,
not a
okay,
variable.
I see.
They also provide the result for the case when M is growing.
Mm, okay, sure. Okay.
Yes. Okay, so that's a when like the the specification where the general adaptation is impossible or possible with the fixed number of source domains. And in case that the general adaptation is possible, some restrictions are considered in the paper, and with some method to estimate the target estimator. And I will present here like the case when the bias configuration is ordered, means that uh, in the definition of the order bias, so H1 smaller than H2 and smaller than Hm. So we know that the first source domain is the most like the closest to the target domain, and the M domain is the furthest domain to the target domain. So in that case, so with the order in the bias, so it's reduce the searching space. So in general adaptation, we need to search for the source domain that are relevant to the target domain and choose them to learn the target estimator. So in that case, we have 2 power m, so the exponential relationship to search for a good set of the source domain. So in the order case, so we only have the linear lines relationship to search for. So to construct the estimator, So they use the intersection base. So we have the estimator title K for all the domains, including the target and the source. So the first thing, they define a prefix estimator titled theta hat of R, means that that estimator use all the domain from K equal to 0 to R. So it's the most like the R most closest domain to the target domain. So that's so the prefix estimator is constructed by the weighted sum of the title theta title K. So the weight is defined by the ratio between the sample size of that domain in relative to the total number size of all the domain in that set. And then with a confidence level, they construct a set of the BR here, means that the set of all estimator that has a smaller that has small distance in comparison to the estimator theta hat, and the radius is defined by the tau divided by the total sample size. So the tau here is the variance. The first term is the variance. And I think, I don't know about the second term. So
it's fine.
if you have any
Come
idea,
from,
so
yeah.
yeah.
It comes from the analysis. It's fine. So they pick that's a difference in the largest T. I see. So they pick the largest T, such that all the
Yes, that's right.
things are still intersect.
So by defining the confidence region BR, so they expect that the two estimator of the target domain are inside that region.
Okay.
And yeah, and the variance bias trade-off. So when we add a new domain, the variance decrease, but the bias increase. So they use the intersection by estimator. Like, I think that they try to have like a consensus between the domains that are closest to the target domain. And when the when all of the domain, not all of the domain, but when they reach the maximum T, when all the domain are intersect with each other, which means that they reach the highest number of the domain with the consensus. And if they increase the number of the source domain, so they don't agree with each other. So it's likely that adding a new one will increase the bias. Why it doesn't provide an advantage in the trade-off? Yeah, so that's, I think, the institution of the intersection by estimator. So with that estimator derived from the intersection based method, so they have the result, like the result here, means that the estimator derived from the intersection estimation method will have like the probability of a large distance to the two targets estimator is smaller than the like the confidence threshold. And the equation 13, it states that the cost of adaptation for the set of the bias configuration where whose the bias in order is bounded by the logarithm factor of the number of source domain, the total sample size, and the d tau squared is the variance.
Theta hat 0, is that from the construction above, right?
Where is the hat zero?
Equation 12.
Equation 12.
That's the intersection estimator.
Intersection estimator.
Yeah, theta hat
So
0 is the equation 12. So that intersection estimator, right?
yes, that's right.
I see. So basically they say that if you do the intersection estimator, then the estimation error would be close to the minimax risk
Yes,
up to some log term and
yes,
constant
that's right.
term for all possible problem P in the problem class H
Yes.
and tau. I see. Yeah, there's something like that we can, some of the ideas here we can think about doing is for uh, multi-source reinforcement learning, transfer learning. But in reinforcement learning, it's harder. So we need to mention, so in the setting of function approximation, uh, you need to construct a version space for multiple sources and do the intersection. So it's also intersection estimator is the useful algorithm approach to pull the data from multiple sources. Yeah, that's something we can discuss later. But it's good. It's good that now the intersection estimator is nearly minimax optimal for pulling the
Yeah.
data from multiple sources. Okay, can you scroll up to the intersection estimator one more time? Okay, here it is. But they have to. I see. Okay. That's
Yeah,
that.
so that's the end of my presentation.
So the main algorithm they have is intersection estimator. That's the main one.
Um, like they have some other algorithm for different configuration. So they have three cases. The first one, the adaptation under order bias, and the second one is the adaptation under like a cluster of source structure, meaning that all the source domains can be clustered into two sets, and they are assumed to be like in one set they are assumed to be close to each other, and they have another case in which the limiting non-informative sources means that they can tell where the distance between a source domain is like is close, whether it's close to the target domain or not by a simple test.
Mm.
So they are three assumption or the configuration they provide the algorithm.
Mm. Um, do the algorithm know the bias in advance? H?
No, no,
They don't need
because
that, right?
because knowing the bias is the only ability of the oracle. So
Mm.
it's the minimax rate, the
Mm.
oracle minimax rate.
Mm. Yeah, that's very interesting. It would be great if we have these sets of results for reinforcement learning, multi-task transfer reinforcement learning, very comprehensive one. If you have that, so basically you solve the transfer learning problem in reinforcement learning. That's very good paper. They consider all
Oh,
cases.
so the oracle, though the true bias for every domain.
Yes.
Oh,
So
okay.
the oracle, yes, the oracle knows the bias.
Yeah, but can you go to the maybe scroll down a bit? Your note. So here, yes, can you scroll down here? Equation 4. So they say
Yes.
that the upper bound, they say there exists some estimator that achieve the error that is similar to the minimax rate up to some constant c. So do they construct a specific estimator for proving equation 4?
Yes, they have. I forgot to present. So the construction of the estimator when
Mm,
the configuration is known,
mm,
it defines the weighted sum of the estimator for target and source domain,
mm,
where the subset of the source and target domain which achieve the value R here. So the R here is the minimum taken by the subset of the source domain. So
mm,
with that set, it's the weighted sum.
that's it. So
Yes.
let's just weighted sum over. Hmm. Oh, so what is H? So it's the subset that achieve the minimum rate.
Yes. So the SH is the subset that achieve the R. So
Okay,
that
I see. They
is
can
the
compute that.
minimum
I see.
the minimum point uh, of the bias and variance trade-off.
Right, but they don't know H. So how can they compute the subset?
They know it because that's the setting with the oracle.
Oh, I see. Sure. So you know H, you can compute the mm, subset minimizer S, and then what? Can you go back?
What? Sorry.
Yeah, can you go to the construction again?
Yes.
Yeah, here. Then basically SH, the subset of the cheating minimum rate. I see. I see. And then they only pull the data from that subset. So that's the idea. Right? So they just compute a subset that minimize the bias
The
variance trade-off. and then
Yes,
they only
that's right.
pull data from that subset only.
Yes, that's right.
So, but
Oh,
when you don't know the bias, so basically you do the intersection, you construct the confidence set, and then you do the intersection of the confidence set,
Yes.
and you only
So
pay the cost of minimax rate, but up to the log time.
yes. So when they don't know the bias configuration,
Mm,
it means that they have to kind of estimate or estimate the subset of the source domains that are useful.
mm,
And in the orders bias configuration, they do that by the intersection method.
mm. I see. So that's the same for, I mean, I guess the main message is the same even for reinforcement learning, right? Transfer reinforcement learning, hybrid reinforcement learning. So you need to know if you know the bias between two environment, then probably you can achieve the minimum rate, but not
Yeah.
then some algorithm to adapt to the unknown bias. That's what we want in the project. But we are working on a setting that a little bit simpler as a starting point. So I see that they also have some non-parametric grades. Can you go to that section? The rates about non-parametric. Well, it makes a Lipschitz assumption.
Um,
Like holders small,
which
the
page?
smallness.
Where?
I think somewhere when you scroll it
Yeah.
down, I see. Can you go some smallness?
You mean the Lipschitz assumption?
Yeah. No, maybe not
mm.
not this one. Can you type smallness? Maybe yeah, maybe here a non-parametric. Yeah,
The remark 17.
yeah. Apply to non-parametric graphics design. I see. Hmm. Okay. So what the result from? Can you scroll up a bit? Okay, that's the intersection estimator. But just see. Can you scroll down a bit? The depth tape.
So that is a proof for the intersection estimator.
Hmm. Can you maybe scroll down to the next page? Oh, they assume absolute holders. Okay. Hmm. I see. So basically, they say that even in the smallness, the intersection estimator also works to achieve the minimax rate. So it's not just in parametric, but also in the non-parametric setting as well. Can you scroll down to the end of this page? Okay, that's it. Hmm. Okay, that's interesting. Okay, any question? I think this set result is very interesting about transfer learning, but of course only for the estimation setting. It's not for sequential decision making. There's no such result in
Could you show me like how they rank the domain if they don't know yet? like how they rank the domain, like
That's an assumption. Like you assume that the you work on the setting where they an order in the bias, so they
oh no no
don't.
no, like after this you show us like how to rank these domain. I want to see.
You mean the choosing the maximum number of the domains that
No no no
are in.
no, like how they choosing the domain to for us, like clustering.
The equation 9.
No no no, in the main paper, like how did they, there are some methods that you show that how to choose the domain. Uh, there's some with clustering something.
Like the order.
In the adaptation under order bias section.
Like for example, they don't know the order for the bias, then they cluster it uh to
Uh,
choose the domain. Yeah.
yeah, that's it.
Oh, okay. And eliminating, how do they choose the cluster? Like they just choose the one that close to the source, or
I haven't gone into that detail.
oh, okay, thank you.
Yeah.
I love that.
So,
Thank you.
Cool. Yeah, we learned something useful today. Thank you. All right. Any other question?
I have a question that why they need to have like smoothness condition when they estimate the cost of the like statistical cost for transfer learning. I still don't understand that.
Ken, do you want to take that?
um, I don't know because it's like I haven't gone into the detail of the proof.
So the smoothness is they have two settings. One setting is parametric, which is the main setting they have. Parametric means that the model you have, there's some latent space, latent dimension, like linear. For example, linear model is it's a parametric case, and I think this they start with just linear model implicitly on the assumption. And then they say that now if you don't consider the linear or the parametric model, you consider non-parametric model like smoothness. Non-parametric means that they basically assume that points that are local to each other, so they have similar value, and the similarity is controlled by smoothness, like Lipschitz Holder's smoothness. And they say that basically even under that setting, then the idea of using intersection estimator also achieve the minimax rate transfer rate. So that's I think that's what they try to say. Non-parametric and parametric are two different settings.
So that's an example for the KN, which is non-parametric estimator,
Mm,
and they have like assumption on the smoothness, right?
mm.
Yeah, I got it.
So you
Oh,
see that
so
equation.
non-parametric is they don't use theta here.
Say again.
Non-parametric means they don't use theta. Like
Yeah, they don't have the parameters.
okay, they use the Lipschitz and something
Yeah,
to measure the closeness of them.
Yeah, basically say that neighbors are similar. That's the
It's like KNN, like choosing the closest neighbor. Oh, okay.
so if you see the equation right above page 21st, they say neighbor are similar. No, it's just right there. Don't scroll. Yeah. Fx minus Fs prime smaller than Ls minus F prime alpha. So that's the way you say neighbors are similar. So if X and S prime are close, then their value are close up to the constant L and the exponent L.
They just use the Lipschitz here, right?
It's not exactly Lipschitz because it's alpha, so they call alpha holder smooth. But if alpha is E1, so it's Lipschitz. It's more general than Lipschitz. So in Lipschitz, it's Lipschitz when alpha equals to 1. But in general, alpha it depends on the structure of the function. So it can be the case that alpha is smaller than 1. So that in that case they call it alpha holder smooth. Function is smooth. There's no parameters. You don't need any notion of parameters. You don't need any notion of theta or the dimension d of theta. All you need to know is that neighbors are similar. That's it. So that is enough regularity to make estimation successful. And they say that in that case, in smoothest condition, so the story doesn't change. You can still apply intersection-based estimator, and then you can achieve the minimax rate. Of course, in the smoothest case, the minimax rate is different. The rate is different. Can you scroll down? The rate when you compute the ratio is different, right? Different than parametric case. But can you scroll down a bit? I think they write the rate. Yeah, so you see the rate is m 2 minus 2 alpha over 2 alpha plus 1. Right? So in parametric case, usually is 1 over square root m something times d, some polynomial function of d. So you have two different settings usually for function approximation, parametric and non-parametric. Okay.
Thank you.
Okay, cool.
Thank you, sir.
No question. Thank
Yes.
you, Khanh. Let's conclude today. See you next week.
Yeah, thank you.
Thank you, Khanh.
Thank you, everyone.
Thank you. Goodbye.